This is a recording by the FMSP for online revision. In this recording we're looking at the AQA D2 specification, January 2010, question 2. This question concerns a group of people, Ron, Sam, Tim, Vic and Zach, who are going to carry out tasks, and in the table we show the time that they take to do each of the particular tasks. We're asked to use the Hungarian algorithm. So first of all, we notice that this has got 4 tasks and 5 people, so we need to put in an extra row in part A of the question. Part B of the question, using the algorithm, we're going to reduce the columns first. So it's going to be column reduction followed by row reduction, and then to find an optimum matching by using the Hungarian algorithm. In part C of the question, it's changed slightly so that Sam is able to complete task 2 in 7 minutes. You'll notice in the original table, task 2 for Sam is given a value X. Well, to do this we have to start off by putting in a dummy task here. So I'll just label that as dummy. We're told that X lies between 8 and 12 in the question. So we need to put this dummy in with the largest value, and that is going to be 12. So along this row here, as long as we've got a value which is bigger than or equal to 12, that will be fine. We were asked then to use column reduction first. So in column reduction, remember that we're taking each of the columns in turn and subtracting the smallest number. So in column 1 we can subtract a value of 8. So that becomes 0, 1, 4, 3 and 4. In column 2 we can subtract a value of 7. Remember that X is bigger than or equal to 8. So the smallest value is 7. And that gives us 0, X minus 7, 3, 2 and 5. Continuing in the same sort of way, in column 3, Tim's column, we can subtract here the smallest value being 8. So that becomes 1, 0, 1, 0, 4. In Vic's column, the smallest value is 7, so subtracting 7, 3, 0, 2, 4 and 5. And in Zach's, we can subtract 8. So 0, 3, 2, 3 and 4. So that was the column reduction. We can now do row reduction. Well, the rows which have anything other than 0 in them are row 3. So we can subtract 1 from row 3, and that will give us 3, 2, 0, 1, 1. And in the final row we can subtract 4, and that will give us 0, 1, 0, 1, 0. The other rows have got 0, so they're going to stay the same. So that finally we have the table as we have here now. So that was the row reduction. If we look at the marking so far, then this was given a B1 mark, just a single mark for getting that dummy row in there. B1 and following through from that dummy. So we get a follow through mark if you've made a mistake with the dummy row there. so that's B1 for the column reduction, a B1 mark for the row reduction, and again any errors were followed through. Now we want to look at the number of lines that are required to cover this, and we'll see that we can cover the zeros here with a line through the first, the second row and the final row and the third column. That will cover all of the zeros. So what we need to do then is to say, well, we can cover the zeros with 4 lines, and that's less than the number of rows and columns, so therefore it's not optimal. So we can't find an optimal solution from this. And for saying something like that, there was an exclamation mark E1. Well, we now have the next stage of the algorithm, which is the process of augmentation. So we look at the table of the uncovered elements and see that the smallest of those is 1. So we can then augment the table by adding that value to intersection points of lines. So adding at these points and then subtracting from all of the uncovered values. So all of these have the smallest amount subtracted from them. Now that's going to produce some more zeros. So if we go through that procedure then and put in the values that we get, the uncovered values, sorry, I beg your pardon, those values covered by 1 line are not going to change. So taking the top row, that will be 0, 0. We're going to add 1 at the intersection. Otherwise, everything stays the same. Likewise, in the second row, we have x minus 7. Still, this then becomes 1, and then 0 and 3. The next row, we're subtracting from all of those that have no line over them. So that becomes 2, 1. The single line there stays the same, 0, and then 2 more 0, 0, 0. Task 4, row 4 becomes 2, 1, 0 doesn't change, and then 3 and 2. And finally, nothing changes in the final row apart from where there's the intersection, so that will go up to a value of 1, the others remaining the same. We now look at the number of lines required. We can see that now there is a 0 in every single row and every single column, so it's going to require 5 lines. So probably just a statement, 5 lines are required, and therefore an optimal solution can be found. The optimal solution will come by looking allocating the zeros. Or you can see, well, there's only 1 0 in the Sam's row, so that means that sorry, I said Sam's row, I meant Sam's column, so Sam must do task 1 there. If you then look at Ron, you can see that, well, Ron can't do task 1, so must be allocated the dummy task there. Moving on from there, you can see that so that Vic must do task 2 because there's only the 1 0 there. Once we've got that, Tim is doing task 4 and Zach doing task 3. So Zach can't do 1, it's already allocated, or the dummy, so that the only one that Zach can do is 3, and therefore Tim must be doing 4. So there's our allocation given that situation. So we need to really write that down, and we can say that V does 2, S does 1, and R was sort of the order that we were doing, and R was not assigned. And once we've done that, T must do 4, and then Zach 3. Right, looking at the marking for that part of the question then, there were method marks for the augmentation, and then an A mark for getting the final table, a method mark for starting off by getting one of either V2 and S1 there, and then an answer mark if your full allocation was correct. Well, to get the total time, we need to look at the original table with the times and transfer our pattern onto that. So we can see that Sam taking 7, the task 4 done by Tim is 8, task 2 by Vic is 7, and Zach doing task 3 is 10. So looking at that gives us a total time of 32. So that the time is 7 plus 8 plus 7 plus 10, and that's equal to 32, and that was minutes. Well, for the final part of the question, we're told that Sam has training and can now do task 2 in 7 minutes. Now that produces an extra 0 in effect, because x minus 7 for Sam becomes a 0, and Sam is indeed allocated that task according to the question. We're asked then to work out the possible ways of minimizing the number of minutes taken, so the possible allocations. Well, if we look at the table then, Sam's doing task 2. That means that Vic must do task 3, and that leaves Tim doing task 4. But we're then left with alternatives, so let's just write down that first bit first. We're told that Sam must do task 2, Vic must therefore do 3, and Tim do 4. But then we've got the alternatives of either Ron doing task 1 and Zach doing 4, sorry, Zach basically doing the dummy, or Zach does task 1. Right, so for that part of the question there were just 2 marks, B1 and B1. That completes this question. You can find solutions to other questions at www.furthermaths.org.uk.